In ancient China, in the Tang dynasty, from the 7th century to the 10th century, there was a flowering and a blossoming of all the arts, and in particular, painting and all forms of decoration blossomed. Now, during this period, the Chinese worked out their rules of art and their rules of painting. And one person in particular, Wang Wei, was very influential. Wang Wei was not only an artist, a landscape painter, but also a poet. And he argued that paintings ought to be like poetry. They ought to use very little information to express great ideas. Now, the Mustard Seed Garden Manual of Painting, which was published in 1700 in China, said the following thing about the use of very little information to portray a great deal in painting. It says, "There are things which 1,000 brushstrokes cannot depict, but which can be captured by a few simple strokes if they are right." And the Chinese said, "Yi tao pi pu tao," which means idea present, brush may be spared performance. You see, the Chinese thought that it was much better if you could paint something without using ink and paint, to show something that wasn't really there, just with a little clever brushwork. The first picture shows a modern Chinese painting because, you know, the rules of Chinese painting still operate nowadays. This is a Chinese scroll painting with clouds drifting around the mountains. But if you look closely, you can see that the clouds aren't really there at all. There's no paint at all on the silk where the clouds lie. The only thing that defines the clouds is the outline of the mountain above them. The artist has used the paint above to pretend that there are clouds present, and a trick of our eye shows us the clouds. Now, in this attempt to find ever more and more economical ways of painting things, the Chinese discovered a very clever trick, and a trick that they passed on to the Japanese, who also used the same principles of art. The next picture is a Japanese scroll painting, a very simple and very beautiful scroll painting by Kei Nen, 19th century Japanese artist. And you'll see that he's drawn a picture of a moon and clouds. And it's really painted with just the minimum amount of ink. In fact, the moon, which appears so much brighter than its surroundings, is only drawn by a thin veil of ink around its edge. There is no ink here or here, and yet the moon appears much brighter than any of its surroundings. What the artist has done is used a gradation of intensity around the edge of the moon, creating an illusion of a difference of intensity between the moon and the background. Well, this trick of defining the outlines of objects was used a great deal in Chinese art and indeed in Western art as well, more recently. The next picture is of a German Christmas card, which shows that same technique to show these two balls which appear to be so different in brightness, the dark one on the left and the bright one on the right. But in fact, the only thing that makes them look that way is the thin black outline of this ball, which lies inside the circle, and the black frame around that one, just a local black area creating an apparent intensity difference. If I cover these up, mask them off, so that you can't see those outlines, I think you'll agree that they're exactly the same intensity. There's no difference at all between them. Only if I take it away does the difference appear. So the brightness difference there is an illusion. It's created not by photons of light, but created inside the eye and the brain. This technique of creating intensity differences purely by outlining was not only used in art by the Chinese, but also in pottery. This is a beautiful Celadon bowl, which was loaned to me by Dr. Impey of the Ashmolean Museum in Oxford. It's a glazed 16th century Ming bowl in which a pattern has been produced by carving into the clay with a wooden device triangular in shape, so that it cuts a groove which is deeper on one side than the other. When the glaze runs into the groove, the parts that are deep produce a dark area, and the parts that are shallow produce a lighter area. Now, if we look at, on the monitors at the thing, I think you can see around this pattern of leaves and flowers, there's a dark border that runs. That's produced by inscribing the clay. And the areas of the flowers themselves here and here appear much brighter than the background because of that same trick of local intensity difference. The trick was discovered very early, apparently, in the history of art. As the next picture shows, this is from cave paintings in Altamira in northern Spain. These paintings were made perhaps 15,000 years ago. And already the artists had discovered the method of applying a graded dark border at the edge of the pattern to create the impression that the pattern itself, the shape itself, was very much darker than its background. So artists have known about these tricks of representation and the illusions created by borders for a long time. The same facts were discovered by scientists only 100 years or so ago. Indeed, it was the great German physicist Ernst Mach who first described, in scientific terms, these illusions produced by differences of intensity at borders. In his paper published in 1865, Ernst Mach wrote, "By chance, I have noticed a phenomenon involving rotating disks with black and white sectors, the further investigation of which has led me to a more general law of physiological optics." Not physical optics. He was talking not about physics, but about physiology and psychology. Mach had discovered what artists had found a long time before him, that local variations of intensity could produce apparent differences of intensity over a very wide area. Now let me demonstrate one of Mach's experiments to you with a rotating disk of the sort that he used. Now you'll see that this disk is half white and half black. If I spin it very fast, so fast the two areas fuse together, you would expect to see just a grey, a uniform grey. So let me do that. There'll be some problem looking on the television screens because of beating with the raster of the cameras, but I think you'll agree that looks a uniform grey. Well now, if instead of that, I use one of the pictures of the type that Mach used, like this, the effect will be quite different. You'll notice that in the center and at the edge, it's just the same as the other disk, half black, half white. But here, halfway across the radius, is a change of intensity produced by the addition of a little bit of extra black on the inside and extra white on the outside. Now, if when we spin this, we were to see it as it physically is, we'd expect to see grey, black, white, grey. But that's not at all what we see. When we spin it, you'll see what you see. A local difference of intensity across a border creates an apparent difference of intensity that extends over a much wider distance. I think when we spin this, it'll appear to be lighter on the outside than on the inside, uniformly darker from the center to that line and lighter on the outer side. Do you agree? The middle appears to be grey, and the outside, if you look at the monitors, appears to be white. And yet we know very well that this part of the image is actually physically the same as that part of the image. The apparent intensity difference is created only by the detection of the change of intensity at the boundary. We'll use another technique now to show you another of Mach's observations, which is almost the inverse of that the eye is incapable of detecting steady levels of intensity if there are changes and edges present in the field. And I'd like to show you this using these 6 candles to cast an image on the screen. Now, each of these candles acts as a light source. Each of them throws light onto the screen and produces a patch of mixed brightness in the center of the screen. If we could turn the lights down, please, right down, then the only light that we'll have present in the theater is the light from the candles. Now, if I move this card across, I'll cast a shadow on the screen. But each candle will cast its own shadow. There will be more light on the right-hand side of the screen than on the left-hand side of the screen because the shadow's coming in from the left. If you look at the shadows, you'll see that there are lots of them. Now, if we could look closely at those shadows, each shadow is in fact an equal step of light. The light intensity is constant across the whole of those steps of this staircase of intensity. But they certainly don't look constant. They look much brighter on the left-hand side of each step than on the right-hand side of each step. I think you'll agree. They don't look like even areas of brightness. Well, those bands of highlight, of bright and of dark, on each side of the staircase are not present physically on the screen. They're created in your eye and in your brain. They're bands of brightness. We now call them Mach bands, after Ernst Mach, which are created inside the head, not by quanta of light. So the appearance of areas of brightness depends very much on what happens at the borders. We seem to analyze the world only in terms of edges and the detection of brightness changes at those edges. The next slide shows a particularly striking example of that dependence of information about brightness on what's happening around an image. This was an illusion discovered by the psychologist Kafka. If you look at it, I think you'll agree that it consists of a grey area of constant brightness. It's the same intensity all around that grey ring with a black and a white area on each side. If I cover up the central line, perhaps you'll see a change in the appearance of the brightness of the two halves of the figure. This grey half ring appears much darker than this half ring. And that's because this one is surrounded by black and this by white. Somehow the surrounding brightness influences the apparent brightness of the grey in the middle. If I remove the boundary, however, they become more similar again. Somehow the brain is performing a constant analysis, looking at differences of intensity. If there's a boundary here, which destroys the evidence that the brain has that this really is one continuous circle, then an apparent intensity difference is created. So edges are all important in perception. And not only are edges and boundaries responsible for our judgment of intensity, but also our judgment of colour. Just as a dark area can make a grey area look brighter, so one colour around a blank area can induce an apparent colour in it. I'd like to demonstrate that to you. Now, we're going to project on the screen with two projectors, one with a red filter and one just producing white light. Therefore, what we should, if we dim the lights, please, what we should see is a pink patch of colour on the screen. A pink light on the screen, a mixture of the red light and the white light. Now I'm going to put a cutout pattern in the beam of the red projector. So what now will be on the screen is simply a shadow, a black shadow with no other colour present. But I think you'll agree that if I move the shape across, you can see it on the monitors as well, very clearly. Instead of just appearing black, it appears green. The red surrounding light has somehow induced the appearance of green in the center. Just as darkness enhances brightness, so redness enhances greenness. There is color induction, just as there's brightness induction in our visual perception. Thank you very much. So our perception of the world around us, of the colors and the brightness levels, depends very much on what's happening at the edges and the borders of patterns. Now, I hope in the next slide I can convince you that if a pattern has edges which shouldn't be there, it can very much disturb our perception. The next picture, please. Now, if you look at the monitors, I think you'll see even more clearly, this is a very hard pattern to decipher and decode. I don't know whether any of you can see at all what's shown in that picture up there. I doubt it very much. Now, if the camera could draw away, could reduce the size of the image, if you watch the monitors now, you'll see the image getting smaller and smaller and smaller. And perhaps at some point, you'll recognize what that picture is. Could we go even smaller than that? Is it possible? Well, maybe some of you are beginning to see what the image is, perhaps the back of the room. Maybe it would help if we came back with the camera again to the picture and asked the projectionist to defocus the image, please. Could you just adjust the focus so that it's not correctly focused, to get rid of those borders and edges? Now again, if we look at the monitors, can you see the image which is there? It would help you, I think, if we looked at the original version. Can I have the next slide, please? That's the original picture from which that strange pattern was produced. There's a picture of Father Christmas, of course. Now can we go back to the pixelated version, please, and sharpen the focus? This picture is produced by a computer procedure called pixelation, or quantization, in which the original image is broken down into a number of squares. Within each square, the average color level and the average brightness level is calculated, and that color and brightness is presented in that square. It's a very simple way of representing the elements of a picture. But one problem is that it produces edges and borders which aren't really there and which weren't there in the original image. And for some reason, this seems to interfere with the perception of the picture. False edges disturb perception. Our perception of the world depends on the detection of the edges which really are there. Well, so far we've heard from artists, we've heard from physicists and psychologists about this phenomenon. It would be nice to know why it happens and how it happens in the brain. Well, physiologists began to play their part in this scientific adventure in the 1940s in New York. Hartline and Ratcliffe began to study the way in which the eye detects brightness and the way that brightness in one part of the eye can influence the signals produced by brightness in another part of the eye. They didn't work on the human eye, they worked on the eye of a very simple creature shown in the next picture. This is a crab, the horseshoe crab. This is a Japanese stamp showing the species of this horseshoe crab, which is found in the Pacific, but it's also found in the Atlantic as well. It has eyes on the side of the shell, and they're compound eyes, rather like those of an insect. They consist of many facets, many lenses, with receptors underneath each lens. In fact, the next picture shows you a micrograph of the retina of the horseshoe crab with a view of the eye above. Here's the eye with its many facets, the many lenses which focus light down onto the receptors. And in the lower part of the picture, you can see the nerve fibers running down from the receptor cells in that eye, down, running towards the central nervous system of the crab. Now, Hartline and Ratcliffe and their other colleagues were able to record impulses from those individual nerve fibers running towards the brain of the crab, while shining lights on one or more of the receptors. And they discovered a quite extraordinary observation, that sometimes the eye responds better to a smaller amount of light than to a more intense light, as we'll see in the following piece of film.
Early research on the horseshoe crab's eyes was done here at Rockefeller University in New York. It's now continued by Dr. Udi Kaplan. From the eye, the optic nerve runs to the brain. Partway along, the shell is removed and the nerve is dissected out. The only connection between eye and brain is this barely visible cobweb-like strand. The nerve is draped over an electrode, which detects any signals it's carrying. The crab's eye sends out occasional electric impulses. They are amplified and played over a loudspeaker. A strong pencil beam is used to focus light on one part of the faceted eye. Immediately, the rate of firing increases. So the eye converts light into electric impulses. The research soon revealed a surprising effect. By chance, the experimenter turned on the room lights. The firing rate went down. It seemed illogical. The eye appeared to respond more to dim light than to bright light. They resolved the problem by moving a shadow across the eye. On the left was the response in the dark. As the edge of the shadow crossed the eye, there was a blast of signals. Then in bright light, the signals went down again, almost as low as in shadow. So the eye did not respond particularly to light or dark, but reacted strongly to the junction between them. In the wild, light-dark boundaries signify the edges of objects or features.
Well, our eye, like the eye of a crab, works in much the same way, responding only to local differences of brightness where there are edges in the field. I mean, it's a remarkable fact that when you look at the sky, there's very little information leaving your retina from those photoreceptors that are actually looking at the sky. In fact, the signals that they're sending to the brain are not very different from the photoreceptors that are looking at the dark ground below. The photoreceptors, the nerve fibers connected to the photoreceptors which are most active, are those that are looking at the horizon, telling the brain only where there's a change of intensity. Now, why does the eye do this strange trick? Well, I think we'll see a clue to that in the next slide. This shows the range of intensities of light that our eye has to handle and deal with. You'll remember in my second lecture I told you about the absolute sensitivity of the eye, the smallest amount of light that could be detected by the human eye. That turns out to be only about 10 quanta absorbed by the photoreceptors under ideal conditions. The brightest light that we can see without damage is a direct view of the sun. Indeed, I should warn you about this. If you look directly at the sun, fixate it for a long period of time, you can actually damage your retina, so don't ever do that. But the bright sun is literally 10,000 million times brighter than the dimmest light that you can detect. So our eye has to operate and deal with signals and patterns over that fantastic range of intensity. Now, no physical instrument made by man can possibly deal with such an enormous range. And yet physical instruments are made of electronic components which are much more reliable and much better at signaling than the nerve fibers that connect our eye to our brain. So our sense organs, all of them, not just vision, have had to resort to tricks to enable them to deal with a very large range of variation in the energy that they detect, despite the fact that they have to use very poor quality cables, the nerve fibers, to send their information to the brain. What they've done in the eye is to signal only where there is a local difference of intensity, ignoring information about the absolute intensity. Now, I've asked the BBC engineers, and they've put a great deal of trouble into this, to help me with the demonstration. Cameras, like those that are looking at me now, have been perfected over the years to deal with a large range of contrast variation. They're nowhere near as good as the human eye at dealing with different intensities, but they're certainly really quite well adapted. If we could look at grayscale, this is something which viewers never normally see. This is something that's used to set up television cameras and to get their electronics adjusted properly. It's a series of grays, and the electronics of the camera can be set up so that each step of gray is perceived as a step by the camera. And if we look at the monitors now, you can see that they're set up quite correctly, as they should be. You can see the full range from dark to light in each case. Now, that's the range of contrast and intensities that the camera could deal with. Our eye could deal with a much, much bigger range than that. But imagine that the cameras could only analyze a small variation in contrast of intensity. What would happen? Can I ask the engineers now to play with the controls and do something which would never normally happen, on BBC anyway, and adjust the intensity value of the camera so that it starts to look only at the black parts. Can you see that the white parts are now all washed out? The contrast range handled by the camera has been shifted towards the black. Now can we shift it towards the bright, please? And you can see that the bright patterns are now being seen well. The whole thing's being seen well, but now the brighter ones are seen, and the darker ones have all just become a uniform black. You see, what's happening here is that the range of available intensities that the system can handle is being shifted backwards and forwards. If the system can only analyze a small range of intensity, the rest of the scene can't be analyzed at all. Well, our eye, if it didn't have the kind of tricks that it does, which artists discovered so long ago, would have a very odd and very distorted view of the structure of the world. Well, not only have artists discovered this trick of producing intensity differences by surrounding an area with darkened light, but they discovered that all you really need to see a pattern is the borders alone. Outline drawings, that's the basis of caricature and cartoon and all forms of sketches, have been used by artists, well, since they first began to practice their art. The next picture shows again from Altamira in Spain, 15,000 years old, an engraving on the wall of a cave showing a very nice picture of a deer, immediately recognizable, yet the animal is only portrayed by a line drawing, by outlines alone. It doesn't look quite like the real thing, but it's certainly good enough for us to know what the pattern is. Again, we can ask for some help from the BBC engineers to see whether they can perform the same kind of trick on this visual scene we're looking at. What they're going to do now is something that technically is called high spatial frequency bandpass filtering. They're going to cut out all the information about absolute differences of intensity between the different parts of the field, and there we are. All that the camera is showing now are the borders and the edges of patterns. You can still see, I mean, it may look like the black and white minstrel show, but you can still see that I'm a person. You can see my hands and my head. You can see the objects around me, but the only information you have available is from the edges of the patterns. Thank you very much. So it looks as though our visual system gets over the physical limitations of its own sensory structure and its own nerve fibers by choosing to analyze only where there are changes of intensity in the visual scene. Well, in the same way that the eye extracts information only about changes across space in the retinal image, in the same way, it extracts information only about changes in time. If we look at a pattern of light which is constantly changing, it's a remarkable fact that our brain is only signaling information, that our eyes are only signaling information to the brain, principally about the changes of intensity. I'd like to demonstrate how useful that can be using the bionic head with which you're so familiar at this stage. Now, you'll remember that the bionic eye in the head consists of... Could we reduce the intensity of light, please? That's good. A little higher now. Can we turn up the light a little bit? You can hear... Okay, that's fine. You can hear how this artificial nerve fiber is popping away in proportion to the amount of light being detected by this eye. If we could look at the oscilloscope screen, you can see the pulses, the nerve impulses at the top, and the signal from the eye below. Now, at the moment, the frequency of impulses is directly related to the signal generated by the photocell, which represents the eye. But this artificial nerve fiber is only capable of firing impulses up to about 110 impulses per second, just like many of the optic nerve fibers coming from our own eye. Now, I'm shining a light on the eye. You can see the way that the nerve impulse firing increases. But as I bring the light closer, the nerve fiber saturates and can no longer respond when a certain intensity level is reached. If I put a pair of sunglasses on the bionic head, it stops firing altogether, and it can no longer respond to light at all. You see, this bionic eye is only able to operate over a small range of intensities because of the properties of the artificial nerve fiber. The cell itself can follow a wider range of intensities. Well, now let's do what the real eye does. I'll switch to a different electronic circuit. This is a very clever electronic circuit which simply differentiates the signal. It only responds to the rate of change of intensity. It ticks away at a constant level. If you watch what happens, I put a light on the eye. When I put the light on, there's a burst of impulses, but then it settles down to a steady level again. If I take the light away, it stops firing and comes back again. What it's doing is signaling changes, not absolute levels. Now the photocell is able to detect changes over a much wider range because the absolute level is subtracted out. And if I put the sunglasses on, initially it stops firing, then it starts to fire again, and now it can detect the light again. And that's because it's getting rid of information about the steady level of light and is only signaling differences. So it's able to extend its operating range. Well, that same principle is certainly used in human vision, and I'd like to ask for a volunteer, please, to help me with an experiment. Could you come down? I'm going to try and show you the way in which our visual perception depends on changes of intensity rather than the absolute level of brightness falling on the eye. Can I ask your name?
Cornelius.
This is Cornelius, who's going to help. Would you like to sit down, Cornelius, about there? Wear a patch over one eye. I'd like you to hold that, if you would, with just two fingers, that's right, and put it right up against your eye, very, very close. So you don't see anything except the light coming in through the ping-pong ball. He's looking through a ping-pong ball with a hole at the back. And you mustn't blink while you're doing this. Can you try and hold your eyes open all the time? All right? And what can you see now? Just a diffuse field. You can't see any pattern at all. What I'm going to do is change the light entering his eye and ask him what he sees. OK, I'm going to shine a projector at you, Cornelius. Could we turn the room lights down, please? Now, I'd like you to tell me what's happening. What's happening at the moment?
Just a light.
Is it bright?
Fairly bright.
Right, OK, if I change it?
It's brighter.
Yes. Anything happening to it now?
Getting dimmer.
It's getting dimmer. OK. And if I do that?
It's dark.
Went dark, yes. OK.
It's bright.
Yes. Is it staying bright?
It's getting slightly dimmer.
OK. Now, what about some colours, Cornelius? What about that?
It's orange.
Yes. Now, tell me if it changes at all.
It's going dark.
It's going dark. Is it still orange?
No.
It's not, OK. And what about this one?
It's green.
Yes. Still green?
It's fading away.
All right. And this one?
That's red.
That's definitely red, yes.
Yeah,
OK.
that's gone.
It's gone. What about if I do that?
It's back.
Red?
Yeah. It's gone.
It's gone. And again?
Back again. It's gone.
OK, that's fine. Thank you. That's lovely. Thanks very much, Cornelius. Well, what we saw there was what vision is like when we convert our eye into a kind of photocell, like the bionic eye. Our eye is only capable of detecting change. It detects change in brightness, change of colour, but if there are no further changes, vision resorts to a strange kind of blank, colourless experience. A very odd experience. You can try it for yourself with a ping-pong ball at home. Well, this must mean if our eye is dependent on changes, our eye must move in order to preserve vision. And indeed, psychologists discovered some time ago that if artificially the retinal image is fixed, if you don't allow eye movements to move the retinal image, vision is very much changed. Can I have the next slide, please? This shows one of the types of apparatus used by psychologists, this is Roy Pritchard, a psychologist, to study what they call stabilized retinal images. It's a very clever trick for getting an image onto the retina and not letting it move when the eye moves. Attached to Roy Pritchard's eye is a contact lens, which is very firmly attached. The lens moves with his eye. And in front of the lens is a stalk and another lens and a screen with an image on it and a little light bulb behind. So Roy Pritchard is looking at that picture through an apparatus which is stuck to his eye. Wherever his eye moves, the picture moves with it. Now, what happens under these circumstances is that initially, when the picture's first turned on, it's seen perfectly clearly. But within a few seconds, it fades away, disappears for good, and never reappears if it's perfectly stabilized on the retina. So our eye movements are necessary for us to see at all. A stable image, a nice fixed image, is essential to be able to see, but it's essential that that image should keep changing all the time, or the world would literally disappear. Can I have the next picture, please? We, in fact, all of us have a stabilized image on our retina, which we never see because it's stabilized. This is a picture of the retina of the human eye, taken with, through an ophthalmoscope looking in through the pupil of the eye. You can see the fovea, that area of great acuity where so many cones are clustered over here. And here, this white spot is the optic disc where the nerve fibers leave the back of the eye. Well, as well as nerve fibers leaving the eye, there are also blood vessels coming into the eye, and they spread all across the surface of the retina. Those blood vessels produce shadows on the photoreceptors below, a pattern of shadows across the whole of the visual field. But we never normally see them under normal circumstances because they're fixed on our retina. They're stabilized, and therefore they disappear from view. Well, I'd like to ask for another volunteer, if I could, to come down and help me with the demonstration. Philip, would you like to come? This is my nephew, Philip. Come on. Come and sit down, Philip. Philip's going to show us how his eyes move. Can you sit on the chair? And I want you just to look at the television camera for a moment, and it's going to look at your eyes, okay? Now, if you'd like just to look just above the television camera, that's it, let's keep this chair still for the moment. Just look above the television camera and try and move your eyes slowly from one side of the room to the other, as slowly and smoothly as possible. Go on, off you go. No, smoothly, Philip. Just try and move them smoothly. Off you go. You see, he can't. His eyes are moving in jerks from one position to another. Try again. He simply can't make smooth eye movements. Well, I should qualify that. He certainly is able to make smooth eye movements. If you'd like to follow the end of the pointer, I'm now going to move the pointer backwards and forwards, and we'll see whether he can follow that. If we could look at his eyes again. You see? His eyes can move smoothly, but they only do so when he's following a moving object, which is actually moving across the field. Normally, when he's looking at the scene around him, he moves his eye from one position to another, as it were taking a snapshot of one thing, then another thing, one after the other, moving his eye frequently enough to avoid this problem of stabilization. You see, it's important to have a fixed image, but that image should constantly change. And there are various reflexes which keep the image fixed. I explained some of them in my last lecture. Let's demonstrate one of them now. If you'd like to look into the television camera, I'm just going to move this chair backwards and forwards. You see the way in which his eyes are moving smoothly to keep his view on the television camera at all times. That's a reflex which is produced by signals from the balance organs in his ear, which I told you about last time, stabilizing the image on the retina until he starts an eye movement of his own. Okay, thanks, Philip. Well, from the beginning of eyes, from the first eyes in evolution, this problem has been faced. How to produce an image which can be moved around regularly, how the eye can scan the world around it. If we look at a very simple eye, quite unlike our own, we find an entirely different mechanism for accomplishing that. The next picture is of a curious little animal called Copelia, about the size of a pinhead, which lives in the waters of the Mediterranean. This is the female of the species. It has two eyes, one on each side, and they're a little bit like a single element of an insect eye. They consist of one lens out at the front of the animal, and a second small lens deeper in the animal with just one poor, isolated photoreceptor organ looking at the image. Just one, acting like a photocell. We might think that this animal would have no image of the world around it at all, that all it would be able to do is detect light. But it has a most amazing trick for scanning, rather like the mechanism in a television camera, scanning the image with its one photocell. What it does is to move the receptor backwards and forwards across the image plane of that first lens. So the receptor scans looking at different parts of the image, as you can see in this next piece of videotape prepared by Richard Gregory and Tony Downing, which shows the eye of Copelia scanning. There's the receptor, and you can see it flicking backwards and forwards, jerking backwards and forwards, looking at different parts of the image, using a scanning principle. And we'll see it in the next sequence in higher magnification, the same receptor, again jerking across the image screen. Here it is, and I think you'll see it moving across. There it goes, the whole receptor being pulled across the plane of the image. Thank you. So this animal has accomplished its analysis of the world by using just one receptor, scanning, rather like a television camera, whereas we use many receptors, looking at the world, then moving to one position after another. Well, all of these tricks, then, are necessary because the eye has to deal with such an enormous range of information. The problem of the dynamic range of sense organs isn't exclusive to the visual system. It's a problem for other senses as well. And I'd now like to demonstrate it for you using your auditory system, using your ears. Thank you, John. Thank you very much. Now, I'd like you to listen to some sounds which I'm going to play you. When the amplifier warms up, if you all keep quiet, you'll hear a tone playing. It's a tone of 2,000 cycles, to which you're quite sensitive. And I'm going to change the intensity. Now, I'd like you to estimate how much the loudness of the tone has been changed. How much louder is the second tone than the first? Could you think about that? All right, now I'd like you to, if you would, to put up your hands when I ask you, do you think that the second tone was twice as loud as the first one? Could you put up your hands if you think that's true? No. 5 times as loud? Quite a lot of people, yes. 10 times as loud, maybe. A few more. 20? No. 50? No. Well, a few 50s, all right. Most people seem to think it's around 10, 20 times as loud. In fact, it's 10,000 times as intense. Cool. The ear is able to deal with an enormous range of intensity, and we make mistakes about the absolute intensity of sounds, just as we make mistakes about the absolute intensity of lights. The light in this room is thousands of times dimmer than the light outside in the streets. It doesn't seem that different. And that's because our eye, like our ear, is so inefficient at providing information about absolute levels. The same kind of processing is true not only for the ear and the eye, but also for the skin. The range of intensities of pressure that our skin has to deal with is equally fantastic, from the 1/1000th of a millimetre, which we can detect under ideal conditions, indentation of the skin, to the sort of indentation that would happen if you slapped one hand with another. We have to deal with that fantastic range. And again, the skin overcomes that problem by signaling differences of pressure rather than absolute pressure. Now, I made a piece of videotape of an experiment to show you this. And what you'll see in this piece of videotape is a recording from nerve fibers innervating a piece of skin from a frog, just an isolated piece of skin, dissected from a dead frog, with the nerve fibers still intact. And you'll hear pulses generated from those nerve fibers. Can I have the videotape now then, please? What I'm doing is touching the surface of the skin with a blunt probe, trying to find what area of the skin is connected to those nerve fibers. And there it is. It's at the top of the piece of skin. You see how well it responds to movement of an object across it. But now look what happens if I touch the skin with a paintbrush, just very lightly touching. And off now. The nerve fiber fires as the paintbrush touches and as it's removed, but doesn't continue to fire while the brush is there. It's only responding to changes. It doesn't signal the absolute pressure on the skin. This makes the system very, very sensitive to movement, but not at all accurate in providing information about the true, real level of stimulation. Well, this must mean that animals are dependent on things moving and changing around them. Can I have the next visitors, please, Bill? These are some frogs. Frogs are very active animals. They're very good at catching worms and flies. They're very, very responsive to small moving objects. But frogs like this literally starve to death if they're surrounded by dead insects or dead worms that don't move. A frog probably really can't see things around it unless those things move. It's completely blind to anything that does not move and will starve to death if it's not surrounded by, if it never sees moving food. Well, our ability to see movement is obviously crucial for our perception of the world as well. The recognition of movement and when it occurs is really rather a complicated process. You may think it's very simple to know that my hand is moving. Obviously it's moving. But if one thinks about the kind of analysis that is involved in detecting that movement, it's really very complicated. You see, if I'm to know that my hand is moving, I've got to perform some kind of analysis on the shape of my hand to recognize that it is a certain object, and to know that when it appears in another part of my visual field, it's the same object which has gone to a different place. therefore producing the sense of movement, rather than one object disappearing and a new one appearing. So the recognition of movement depends on the analysis of shape and pattern and on the positions of patterns and the sequence of those positions. In fact, our eye, rather like cameras, seems to work on the basis of integrating or summing information constantly, and we're able to recognize movement on the basis of the presentation of static patterns, one after the other. If we weren't able to do this, then we couldn't have things like television cameras or cinema. The basis of cinema is the perception of movement from a series of static pictures. I'd like to demonstrate that to you now, the way in which your eye is able to perceive movement from stationary images. I've got here a stroboscope, which is a light, a very, very brief, intense light, which can flash at a variable rate. And I'm going to stand over here. If we can turn all the rest of the lights down, please, all the rest of the lights off completely, so that you can only see me by the stroboscopic light. Now, at the moment, there'll be problems, by the way, seeing this on the television, because the camera has a certain integration time, which tends to produce fusion of the successive images. But I think if you look at me now, you'll be able to see the movement quite clearly. What's the rate at the moment, Bill? About 60 cycles. So you can see the movement quite clearly when there are 60 pictures a second, 60 separate pictures. Now, could we reduce the rate, please, a bit, Bill? Now, if you continue to watch me, I think you'll find a very strange thing happening. About that sort of speed, if I jump up and down, perhaps. Yes, what you're seeing now is a series, perhaps even slower, Bill. Could you turn it a little bit slower than that? Okay, a series of static pictures with no apparent movement between them. Again, if I could jump up and down now, it should look very peculiar, I think. Okay, thanks, Bill. So that shows the way in which the eye, as long as the interval between successive pictures is short enough, the eye is able to integrate and pull those pictures together and to see them as if they were movement. Well, the principle of creating apparent movement by stationary patterns is the basis of cinema techniques. Experiments have been done by psychologists on these phenomena for a long time, and I'd like to illustrate one of them now, if I may. Yes, okay, thank you. Could I have the Vive on, please, Bill? This is a set of lights that can be turned on and off in a certain sequence, in a certain pattern. Fine. Thank you very much, Bill. Thank you. Now, if I cover one row of these and simply turn the switch to switch them on, could we turn the rest of the lights down, please? If you watch the monitors, perhaps you'll see this better. All you see is a series of lights flashing on. They're never on at the same time, by the way. One is on, then the next one, then the next one. But you see it, I think, as a very clear sequence of steps with a moving light moving across the picture. If I now cover those and show the bottom row, which are flashing at the same time, you see that they move in the opposite direction. Now, Bill, could you bring your card in and we'll cover all but the central four. Now, we're still looking at the same sequence of lights, but the movement's quite different. Now what you're seeing is two lights, and they seem to move vertically from one to the other. Could I have the lights up a little bit, please, that I can explain? What we see, I think, is this light moving to this position, this light moving to this position, because of the sequence in which they're being played. And now if you can turn the lights down again, please. Now, if we take away both of the cards, you see really quite a complicated pattern of movement when both of them are exposed. I think you should see one line going up, going along, up, and then back again. So the pattern of movement that you see, although the physical stimulus is identical, depends on the spacing of the lights and the sequence in which they're played. Thank you very much. Well, as I said, this is the basis of cinema techniques. Let me show you a very early example of cinema methods. This is a machine called a zoetrope, which was invented by the physicist Maxwell. It consists simply of a drum which can be spun round and round with a series of slits on the outside through which you can look at the pictures on the inside. And actually the pictures inside this zoetrope are by Muybridge, and they show the positions of horses during galloping, a series of successive silhouette drawings of horses. If we could now look in through the slits with the camera, please, I think you'll see that as I turn, if you look at the monitor, as I turn it round, each slit sees one horse and then the next. So if I spin it fast, well, that goes backwards. If I spin it this way, I think you can see the horse galloping along. What you're seeing is successive images, one after the other. The first basic demonstration of the cinema technique. So then perception of the world depends on the recognition of differences. Everything about our perception of the world is relative rather than absolute. Can I show you another demonstration which I think will show you the way in which the perception of position and of movement is a relative process. Could you project onto the screen, please, Bill? What I'm going to do is project onto this screen a spot of light. Now, if you look at the spot and dim the room lights, I'd like you to ask yourself, particularly if you look at the monitors, what's moving? Is the spot moving or is the screen moving? You may see some hint that the spot itself is moving. Well, in fact, the spot's absolutely stationary in space, the spot simply being projected in one direction. What I was doing was moving the screen around it. The brain then was faced with a signal telling it that there was a difference in movement between the screen and the spot. And it made the mistake of assuming that it was the spot that was moving. Again, it's dealing with relative signals, not with absolute signals. Well, if our perception of the world depends on the detection of relative differences between detectors, what should happen if one of those detectors should fail? If one amongst the set of all detectors should fail, then our perception of the world will be very much disturbed if everything depends on a balance of activity between lots of different detectors. Well, it is possible, by using tricks, to produce a failure of various sets of detectors in our nervous system. I'd like to show you that with this method. What I want you to do is to look right at the middle of this circle while I spin it. Look exactly in the center, please, of the picture. Just keep looking either on the monitor screens or directly. You at home as well with the television, just look right at the black dot in the middle of this spiral. Now, I'm spinning this spiral, and it will be stimulating detectors in your visual system which respond to movement inwards towards the center. Okay, what you're seeing is constant movement inwards created by that spiral. Everything seems to be moving in all the time. And this will cause a failure, a saturation, a fatigue of those movement detectors that respond to inward movement. Now, if afterwards you look at something else, perhaps your vision of it will be disturbed because your outward movement detectors, your expansion detectors, if you like, will be relatively more sensitive than your inward movement detectors. If you could now transfer your gaze, please, to my face. Well, I'm sorry about that. I think you should have seen a sudden expansion of my face, which I can assure you was illusory, produced by disturbing the detectors in your brain. Well, let's see if we can produce something else in another sensory system. I didn't need another volunteer for this, please. Would you like to come down? Now, what's your name? Dania. Okay, Dania. Dania's going to help us with a demonstration of how good her ability to detect temperature with her skin is. Now, would you like to sit down? That's it. Now, we've got glasses of water here. Would you like to put the blindfold on? Perhaps you'd like to take your glasses off. Yes, just put them down on the bench there. That's it. Now, let's put the blindfold on. Okay. Now then, what we'd like to do is to get you to put your hands into these two bowls, please. Just put them in, right in, and let's pull your sleeves up. That's it. Perhaps you can put the tray a little bit nearer or put the glasses a bit nearer. Yes, just put them right in. That's right. And that one too. And I want you to tell me which is hotter, the one on the right or the one on the left?
Left.
This is hotter than that one, is it? You're absolutely sure about this?
Yes.
Is it a big difference? Is it much hotter?
Much hotter.
This one is much hotter than that one is. Now I'm going to put your hands into the other two dishes. Okay, this one into here, and this one into here. Now which one's hotter?
The one on the right.
The one on the right is hotter now. All right, keep your hands there, please, and just look at what's happening. They're both exactly the same, but the temperature difference was created by having fatigued her temperature detectors. She'd upset the system by exposing this one to a cold stimulus, and this one to a warm stimulus, producing an apparent difference that wasn't really there. Thank you very much, Daniel. Well, our perception then of the world depends on the detection of difference. And I'd like to show you a nice illusion that shows that that is true for our detection of shape as well. This is a very well-known illusion. If we could just look at this for a moment, that background pattern just consists of a set of tilted lines. And here, a pattern of lines which are perfectly parallel, regular white lines which are parallel to each other. But if I slide them in on top of the other one, I think you'll see that they, at a certain point, stop. Perhaps I've got this the wrong way around. Yes, I think I have. All right, there we are. Now, perhaps you'll see that the lines aren't parallel after all. And if I move them across to a new position, they change again. So the appearance of the angle of those lines depends on the angle of the background lines. Again, what's being done is the estimation of differences rather than absolute levels. Our perception of the world, then, is a constant search for change and for difference. And when the differences aren't really there, our brain almost invents them for itself. Could I have the next slide, please? This shows a very familiar picture, a reversing figure. I'm sure you've all seen this before. If you look at this picture for a while, first of all, you can see it as a cube with this face pointing towards you. But perhaps if you carry on looking at it, it changes to a cube with that face in the front. There is no real difference in the pattern, but your brain, in its search for difference, invents differences that aren't there. The pattern seems to change regularly. Now, the next picture is an 18th century bust of Voltaire, the philosopher and writer, by Houdon. A very nice, real picture of Voltaire. Now, if I could have the next picture, this is another painting of that same bust by the artist Salvador Dali. If you look clearly, you can see very clearly the bust of Voltaire looking at this lady over here. But is it really a bust of Voltaire? If we come a little bit closer with the television camera, if you watch the monitor, I think you'll see that hidden inside the bust are two little figures with ruffs on, with white ruffs. The bust changes to something else as the brain searches for new meaning. Again, if we could defocus that picture, please, if the projectionist could slightly defocus it while you watch the television monitor, maybe the bust will reappear again. You can see it as one thing or as the other thing. And sometimes it changes from one to the other spontaneously as your brain searches for meaning. Perhaps the best known example of these sort of double figures which change from one thing to another is that familiar illusion in which you look at a vase and you can either see it as a vase or as two faces. You know the trick. Well, this is a real vase. It's a very nice vase produced by the Kaiser Porcelain Company to celebrate the Silver Jubilee of the Queen. And I think it would be nice if we could show that vase illusion with this real vase. So, Bill, do you think you could take it outside? What Bill's going to do is to hold that vase in the projector beam so that we can see the outline, the silhouette of the vase. And we should perhaps see two faces as well. Now, if we could look perhaps on the television monitors, if the camera zooms in to a closer angle, we should see very clearly those two faces, one on each side. But now, Bill, if you turn it through 90 degrees, perhaps you'd see why this particular vase was produced for the Silver Jubilee. If you look closely, I think you might actually recognize those two faces. Thank you, Bill. Well, then, our view of the world depends very much on the detection of change. But as many of these illusions have shown you, if you present the brain only with changes, it can make mistakes about absolute levels. And this can lead to disturbances of perception, not only for vision, but also for hearing. I'd like to finish this lecture by showing you a remarkable piece of animation produced by Ian Ames of an Escher illustration, the artist Escher, and it's combined with a very strange sound. I'd like you to listen to the sound as you watch the picture and think about how many notes there are on a piano scale. Well then, our brain depends on the detection of difference, and it's only illusions like this that create misperceptions of the world. Vive la différence!